Welcome. I would like to welcome everybody to TIES webinar series. So let me say a few words about what TIES is. So TIES is more than 30 years old. It's called the International Environmental Society under the roof of International Statistics Institute. And the primary goal of TIES is to strengthen the connection between statisticians working in environmental sciences and the main knowledge disciplines in a broad sense: atmospheric sciences, ecology, hydrology, and so on. So everything that relates to environment. The idea of this series is to make the synergy between statistics, machine learning, and data science and environmental sciences much stronger. So we decided in this, COVID world to use what pluses COVID-19 has brought to us, and that is in particular virtual meetings and webinars that can connect us. And today we'll have our first TIES webinar on data science for environmental sciences. And I would like, before we'll proceed to the speaker, I would like to thank the committee, that is Nathaniel Newlands from Government of Canada, Ignacio Segovia Dominguez from University of Texas in Dallas and GPL, and Yuju Chen from Princeton University, okay? And the idea is that, and of course the students, Zhirei Zhang, Mai Chen Huang, and Tian Zhang, who were invaluable assets in preparing everything on the technical side. I would like to say that we'll start firstly from meeting every month, and the idea is that we'll go to bi-weekly or weekly series. Okay, thank you. And Ignacio.
Yeah, thank you, Julia. Thank you so much for such kind words. This session consists of 40 to 45 minutes presentation and 10 to 15 minutes for questions and answers. We are so glad to present our first speaker in this TIES seminar series. Dr. Kyo Lee is a distinguished data scientist in the uncertainty quantification and statistical analysis group at the Jet Propulsion Laboratory in Caltech. He has a PhD in atmospheric sciences from the University of Illinois at Urbana-Champaign. While studying atmospheric sciences, Dr. Lee became very interested in statistics and has also extensive experience with stratospheric dynamics, neural networks modeling for satellite remote sensing, atmospheric chemistry, and air quality modeling. His papers has thousands of citations and has collaborations with dozens of scientists around the world. So, dear Kyo, thank you so much for accepting our invitation and making time out of your busy schedule, and welcome.
Hey, yeah, thank you so much for the nice introduction, Ignacio. Which screen I'm sharing? Do you see my PowerPoint? Or?
Yes, we see your PowerPoint.
Okay. So the full screen, not the presenter.
No, we see the other one. We don't see the full screen. Yeah, now we see.
Can you see the?
Yes.
Okay.
Thank you.
Yes. So yeah, hello everyone. So yeah, my name is Kyo Lee, and I'm a data scientist at Jet Propulsion Laboratory. In 2020, right before the pandemic, I had a great opportunity to learn about topological data analysis while working with Professor Yulia Gal, and now Professor Dorcas Ofori-Boateng at the Portland State University. Today, I'm presenting this work, as you see in the title, application of a topological data analysis to multi-resolution matching and anomaly detection. This work is still, I'll say it's in infancy. However, I wanna with this talk, I would like to say that topological data analysis has enormous potential for numerous earth science applications. The animation shows at the top of the slide, shows the temperature map during the extreme cold wave in mid-February in 2021, so about a year ago. And these are maps of near surface air temperature from NASA's Geospike model. And this is a satellite climatology, for the 5 days between February 11 and February 15th in 2021. I know, pretty much all the audiences know much better about topological analysis than me, but let me just start with a very brief introduction of the topological data analysis, a TDA. Topology is the study of shapes, and this is some sort of a standard the pipeline of a TDA. By applying a TDA, we can analyze key features of a spatial data or time series. And TDA characterize the shape of a data by using a filtration algorithm. And with and this filtration algorithm, they apply a simplistic complex around each point in the point cloud data. And these shape characteristics include the connected components and first dimensional loops, and depending on the data, it includes a high dimensional holes as well. And the nicest thing that I really would like to leverage in my use case is that TDA offers a compressed representation of the data with complicated shape. And this is really important for earth science application. Okay, then what are the benefits of TDA? All of these three benefits are important for earth science very applications. And we know the topology studies shapes in a coordinate free manner. So these three green ellipses are topologically same. And I will show you a real world example in the atmospheric science why this property is really key. And we all know that topological properties don't change under smooth deformations. And one good example is these same TDA written in different fonts. And these are all topologically same as well. And I already mentioned in the previous slides. So this is really important in earth science applications. TDA, and this is my my colleagues and I try to apply TDA with earth science data. We have done extensive literature review and found only few recent papers on TDA application to earth science. The interesting thing is that the first one was published by our friend, Professor Noel Cressy from the University of Wollongong, Australia. Actually, Noel sent me email yesterday morning after he got the announcement about this seminar. And he introduced his early work on topology, on analyzing the topology of frontal precipitation in North America. And although he cannot make it today's seminar because it's 4 a.m. in Australia, he said he's really looking forward to the YouTube video of the seminar. And this second study published in 2019, it's an example showing how TDA benefits the machine learning using earth science data. what they did here is they applied like TDA like to summarize atmospheric like river patterns. So atmospheric river is like a narrow band of water vapor, yeah, and it transports like moisture like from the tropics like to the mid latitude, and sometimes it's called as it's the nickname of like a Pineapple Express, and it's critically important for the water resource management in the Western United States. What they did is like, they applied like a TDA and like then like trained like their like support like a vector machine, and using and the trained model like can detect like whether like a certain pattern is like gonna be like AR, atmospheric river, or like this is not like AR. So, and this is one good example. And another paper, the lead author of this paper was a high school senior. It's very surprising. And when the published, even the paper was published, like she was still like a high school senior. And this actually demonstrates that like a TDA application to earth science doesn't have to be really complicated and like difficult. And last year, like our work was published using, we applied the TDA to comparing like a different like a data set, and if time allows, like at the end, like I will briefly talk about like this paper like as well. In our work, we try to answer this question. Yeah, seems like this is you know, like kind of like a doesn't really look like a scientific like a question like that much, but this is you know, but this question is very important. It is because almost all of like a climate scientists, including me, have been using like these old school matrix like a bias and like a root mean square like a deviation and pattern correlation, and when comparing like a spatial patterns between different like data sets. And this Taylor diagram has been the community standard like in especially in climate science for the last 20 years since Dr. Carl Taylor published like his paper in 2001. So it's been like over like 20 years. And if you wanna like publish any paper to earth science like journals like and compare and you are comparing like a spatial pattern, you are almost like supposed to include the Taylor diagrams in your paper. And there were some people who took approaches different from Taylor diagrams. The spatial forecast verification methods intercomparison project at National Center for Atmospheric Research, they aimed to analyze and evaluate spatial patterns in meteorological variables from weather forecast models. I highly appreciate like this project because the conventional like matrix based on pixel by pixel comparison of values are very sensitive to the like exact location and deformation of like a key pattern, which I'm gonna talk about like in the following slides like as well. And in this project, like they provide like 4 different like ways to compare spatial patterns between observations and weather forecast model. And I mean, like, and this is, I mean, like a really, amazing like approach. Like, however, there is a like problem. And for quantitative like a comparison of like spatial patterns with different data set between data sets with different spatial resolution, even in their approach, they have to remap the data sets all into like the common like a grid point. And I would say one of the biggest advantage of like our TDA-based methodology is that we don't have to remap the data set. And also the TDA can take care of all of like these. So when evaluating like spatial patterns, well, we are climate scientists always like evaluate like the climate numerical models. Yeah. So when we evaluate the spatial patterns of the simulated by numerical model, sometimes an exact location of certain patterns really matter. So on the left, you see these like a spaghetti like a plot of a hurricane track forecast. Here, performance of simulation needs to be measured by comparing the observed hurricane tracks and these like simulated ones. In contrast, on the right, you see sea levels during the El Nino in 1997 and 2015. And both of these are known as extremely strong El Nino. In El Nino years, actually, like these actually maps, these visualize the sea level height, like the anomalies. And El Nino years, like the sea surface, both sea surface temperature and sea level height, like become higher over tropical Eastern Pacific compared to like normal years. And the location of like these like so-called like wormhole like changes in every El Nino. But what we all know is that both of these are like the El Nino patterns. And if this were like from a like climate model, for example, and the other like were like the observation, we would never say that these model like didn't reproduce realistic El Nino because the wormhole's locate. But as you see, the wormhole's like a location is like a slightly different from each other. Then, what about like a slight deformation? So here, like a deformation includes like a stretching, like a shrinking, or like a rotation of like a spatial pattern. And the answer is no for like both hurricane and like El Nino cases. Let's assume that like this were like observed like a hurricane. And if there were a model which can simulate the hurricane, like this, like somewhat deformed like a hurricane. And if there were a model like this, all of us, like the meteorologists, would think this model did like an excellent job because like the location of the center of the hurricane does really matter, but not like the exact like shape of the like hurricane. And the wormhole like shaped like this in 1997, and in 2015 there exists like a wormhole, and no one cares about like these like a slight deformation of the Eastern Pacific like wormhole. We all care about the like intensity of El Nino. So the main objective of this work is to build a robust and reliable methodology that compares spatial patterns from different like sources. And specifically, like we assess the two temperature like data sets in February 2021 and between June 16 and like July 15 in 2021. And MERA-2 date reanalysis, you can think like this as like the ground truth like observation. And this MERA-2 reanalysis has a relatively high spatial resolution of like 0.625 by 0.5 degrees. And we compare the daily mean temperature from this MERA-2 with temperature climatology from the Earth. So for each day, like so in each day of like February and like each day between June 16 and like July 15, the daily climatology from these satellite observations over the last like 17 years like was calculated like by averaging like the previous historical observation for the 17 years. And we also, and their resolutions are different because this satellite observation has a lower resolution than the MERA-2 observation. Oh, one thing like you might want to remember is like this climatological data, long-term average, doesn't include the anomalous temperature observation in 2021. We also used this MERA-2 data, regraded into this low resolution from the airs to compare our TDA-based metric with the conventional matrix. For those who live in Texas, the second week of February in 2021 was a nightmare. It is very rare to see this like Arbota clipper, like the polar like air, like pocket of like a polar air, like expands all the way down to like Texas. And these two nighttime images of the Houston, Texas were made by combining observations from like OLI instrument on Landsat 8 satellites, plus like a beer sensor like on Suomi MPP and some of the climate like alpha. The difference like here shows like many people, numerous people suffer from the like a blackout. It's and the analysis domain of the cold wave case in February of 2021 is this gray box covering gray plains. And now these are like the maps of like a temperature, and the unit is Kelvin. The top row is from MERA-2 reanalysis. So these are like the almost the actual observations of temperature during these 5 days. And the bottom one shows the climatological like a temperature. And obviously like a temperature during the like a cold wave like was exceptionally like low. And at this point, if I show this, I mean, the actual observation and climatology, something we can call like a normal, like a temperature, everyone wants to see the temperature difference between these two. But I couldn't draw the difference like a map by subtracting this high resolution observation data from the climatology data. What I had to do is I needed to regrade MERA-2 into like airs grid points like first, then we see the like a temperature like a difference is from the climatology, like it's more than like 30 degrees over the like a Great Plains during the cold wave. This slide illustrates the mechanism of like a cubical complex filtrations and how to obtain persistent diagram like from temperature maps. A map of the gridded temperature data can be viewed as a two-dimensional array, which look like this. Here, we change the temperature threshold values and shade the grids whose temperature is like colder than threshold. And you see the like bursts and like deaths of like different cubical complexes. For example, like there's a one like a connected like a component like at the beginning, and like as the threshold like increases, like these like two holes are like a bone, and like at the and the threshold like becomes like over the like a maximum value like among these like 16 values, like nothing survives like except the I mean like one single like a giant like the connected component. And so the spatial pattern of these like 16 gridded data is summarized on this persistent like a diagram. In the filtration like a process, we can use like other complex. In our case study, my colleague, Professor like Matthew Dixon, like from the Illinois Institute of Technology, like applied lower filtration to the same like temperature data. And not surprisingly, the result is like same as cubical complexes. And lower star filtration, similar to like cubical complex, it's appropriate for like a gridded earth science like data because the filtering is based on the value at each pixel. So this temperature map on February 15, 2021 shows a diverse shape characteristics as we change like a temperature threshold like values. And the birth and like death of like each shape characteristics. So shape characteristics, in other words, like a topological like a summary, is displayed on a persistence diagram. So we characterize the shape of like these two temperature maps. So the top one is the actual like observation in February of 2021, and the bottom one is the climatology, the normal temperature, which is expected like in February. And we get the like a persistent diagram like from like each mass. Then if we have a persistent like diagram, we can calculate the difference between two persistent diagrams. And we use the like a Barshestein like a distance here like to measure the like difference between two persistent diagrams. And later in my talk, I will show the Barshestein distance represents difference in spatial patterns and can complement the conventional matrix such as a bias and like a root mean square deviation. So we all know that also now these are like the temperature maps like for the entire like February, and this is from the observed data, and this is a regraded observation. So this high resolution observation is regraded into the low resolution climatology data, and these are like the climatology like map. So we all know that like the root mean square deviation, the RMSD, can be calculated only between these regraded data, regraded observation, and climatology. So the climatology like looks like this, and like throughout the that month, and it's not surprising because it's like a long-term average. Oh. All right. So in contrast, like once those temperature maps are summarized like into persistent diagram, we can calculate Barshestein distance like between these two and like these two like as well. So the resolution of the original data really doesn't matter. Here, so the blue line at the top represents daily mean temperature average like over Texas only. And the green line here is a root mean square deviation between observation, the observation in February 2021 and climatology. And the red line is the same difference, but it is Barshestein distance between observation and climatology. And the orange line is the Barshestein distance, but this is the Barshestein distance between regraded observation and climatology. And this is a scatter plot, this scatter plot indicates that the RMSD, and Barshestein distance, second order Barshestein distance, they are not fully consistent like each other. Temperature was lowest, the average temperature in Texas was lowest on February 15, and both RMSD and Barshestein distance are largest on the same day, meaning that the difference the temperature map from Earth's climatology is largest. So at least there's some consistent parts, but there are some differences as you see here. And unlike RMSD, the Barshestein distance plot is not symmetric, with respect to like February 15th. Like look at this like red line here. This indicates that somehow TDA distinguishes the pattern difference between and after the record-breaking low temperature in Texas that occurred like on February 15th. And this black line shows the temperature averaged over northern part of Great Plains. So northern part of Great Plains like includes like North Dakota, South Dakota, Minnesota, and like Iowa. And can you see like the difference like between like these two? So for Texans, like the cold like a surge, like the coldest day was like February like the 15th, but the cold surge occurred like earlier in northern Great Plains like than Texas, and they lasted longer. And this is now a scatter plot between daily temperature. So x-axis is daily temperature in Texas, and this is a temperature in northern Great Plains. And these numbers are days in February in 2021. Here, I did a really quick and dirty clustering. I didn't do any calculation, just made like these circles and grouped it like a date. So there are like 4 days from 11 like through like 14th are grouped together, and these like 5 days between like 16th and like 20th like of February are grouped like together. And yeah, let's check the difference like in actual temperature mass like between these like two groups. So we can see like a clear like a difference like in spatial like patterns. And then why the RMSD between like these like the two, so before the like the Texas cold temperature and like after the like Texas temperature, why RMSD did not reflect like this like a difference? And if you carefully like look at the map, I think the TDA like the Wasserstein like difference like is mainly due to this like bullseye in Colorado. Can you see this? And in many parts of domain, the temperature was like going up after like the February like 15th, but not in Colorado. And without the like a bullseye of like a cold temperature like in Colorado, this map on like February like 13th is actually topologically more similar to climatology like a map compared to like to the other days. For each of like these like three groups, like we calculated we also calculated the Wasserstein distance within each group as a measure of like day-to-day variability in temperature. Here, I'm showing distributions of RMSD on the top and the second order Wasserstein like a distance. So these are like within group like differences of within group like distributions of Wasserstein distance and like RMSD. And these like blue, green, like yellow dots represent like the individual like value. And we see that regridding. So this is from the original observation, and this is from the like regridded observation. Regridding like doesn't change like RMSD like that much. It's almost the same, and like that. I mean, it will be more surprising if we see like some difference in RMSD after due to the like regridding. And but in contrast, like regridded like the observation, their Wasserstein like distance variability is like smaller than the original like observation. And this is because of the smoothed like spatial patterns. And this also indicates that like the regridding process must have like removed some of the some of the topological features in the original high resolution data. And the Barshstein distance between, we can also calculate the Barshstein distance between the original data and the regraded data, and it reflects some difference. There is a difference associated to the spatial resolution of the data. So in the previous slide, I showed really quick and dirty clustering, but actually my colleague, Professor Matthew Dixon, he has applied different clustering methods to these 28 PDs for the temperature over Great Plains in February 2021. And not surprisingly, there are clear differences between these days, inside yellow rectangle with anomalous low temperature, and the rest of the day. The red dots here represent zero dimensional components, and blue dots for the first dimensional component. And these are centroids persistent diagram for the two groups. And you can also see the clear difference in the distributions of zeros and first dimensional components. A takeaway here is that we can use topological information for extremely efficient and reliable anomaly detection. So now let's move on to another case study, 2021 Western North America heat wave. And this is my analysis the domain. And this heat wave over Western North America occurred by the omega shape, the blocking pattern from late June through mid July. Again, this blue line represents daily mean temperature average over the entire domain. And this green line is the root mean square deviation between observation and climatology. And the red line is the Barshstein distance between the observation and climatology. And due to and you see that the change temperature and RMSD, their change is somehow gradual. So because of this gradual up and down, it's kind of tricky to define onset of the heat wave using the mean temperature or RMSD. However, if you see this red curve, there's a sudden change in Barshstein distance, indicates, well, there's something started at this point and it ends at some point. And in the following slide, we'll see what happened around June 24, when the Barshstein distance indicates that there's a huge topological difference between the observed temperature map and the climatological temperature map. So between June 24 and July 2nd, both especially the average temperature, this the red curve, and in the previous slide you already saw that the root mean square deviation, they just change very smoothly. However, this temperature map on June 25th is topologically very different from the previous day's map. And I think PDA detected this anomalously high temperature in eastern Washington state and use it to characterize a spatial pattern of a heat wave. So as far as we know, there's no quantitative matrix to measure difference in spatial patterns between Earth science data sets at different spatial resolution. In our work, persistent diagrams summarize the temperature maps during the extremely cold and heat waves in 2021. And we are confident that partial time distance between persistent diagrams can be a unique alternative like for the conventional matrix and Taylor diagram, because partial time distance can be calculated without regrading data set. And PDA, and this is, I think, a really important takeaway message. TDA enables advanced and efficient anomaly detection by reflecting high order variability in spatial like a pattern. And applying like a TDA to earth science data has like enormous potential because we can analyze key spatial structures in the even like a three-dimensional like a sounding data and compare them with some climate simulation. We can also examine like a sensitivity of partial time distance like to spatial resolution. And we all know that like a noise reduction on persistent diagram space is also doable. And of course, like the topological representations like can be utilized like in machine learning. And with my in my recent work with a graduate student from like Oregon, we used like self-organizing math a lot. And as far as I know, like self-organizing math is the most widely used machine learning method like among climate scientists like these days. In the past, it used to be like a PCA. Now self-organizing math is a really trendy like a methodology. And in their application of self-organizing math, they tried to find like some weather patterns, like a large scale weather pattern associated with some extreme like weather events like at the surface. And the way like they group like those weather patterns into like a certain number of the centroids, so-called like those self-organizing like a map pattern, they all calculate the Euclidean like distance. But to calculate those Euclidean distance, if data sets are like at all like different spatial resolution, they have to remap every single data set like into the like a common grid. And I do see like a huge like a potential application of TDA and partial time distance based like a distance measure. So thank you for listening. I will take any questions.
Thank you so much for this very interesting presentation, Kyo. Is there any question from our audience or participants? You can write this in the chat. You can unmute yourself if you want. That's okay. Yeah, Sarah.
Yeah, I really have a question about the persistence diagram. It lacks the spatial component. It just gives us some kind of a consistency pattern between, let us say, two data matrices, which probably generated these shapes. But I think the spatial pattern is very important to be included somehow in such diagram. What do you think?
So I think I couldn't understand like so do you think this persistent diagram do not reflect some spatial patterns here?
Well, I think you have probably to link it to the map somehow. And in the original, in one of the examples that you described, you was talking about a clustering. And if you have a clustering for different things, then you might be able to have some kind of persistence diagram associated with each cluster, because the boundaries of the clusters keep changing when you move along in time. If we are talking about one system and we are following it, then it might be interesting to try to see how the spatial diagram is associated with your persistence diagram.
Oh, yes. I totally agree with that. Yeah. So this is I mean, for example, all of each persistence diagram is like for the snapshot of the daily temperature map. And here we didn't really consider the temporal component. So these with even the clustering algorithm really doesn't know that these patterns are from the consecutive days. Yeah, but yeah, our follow work is considering those the time series and changes in temporal domain by applying a zigzag persistence.
Yeah, I think it's quite interesting idea just to have the persistence diagram. Like you can even have some, a surface where you have in one surface indicates the spatial better, and the other side, the other coordinate indicates the spatial, the pattern of the persistence diagram. But you gave a very lovely talk. It's wide ranging and I enjoyed it. Thank you.
Thank you. So yeah, I see a question on the chat window. Yeah, the computing pH, yeah, of course, it could be computationally challenging. And these complexes VR complexes, they may be really computationally expensive if you use these data from 1,000 grid points. But one biggest advantage of the cubical complex is actually computational expense is almost you can ignore. It's very fast and efficient.
May I ask which software is that?
We are using the Goody, the
Goody,
Python.
okay.
Yeah, Goody and.
So when you are actually comparing two images, are the point cloud basically the location and the temperature as a 3 vector? Then you are comparing those.
We don't really. So in our comparison, the location really doesn't matter. So, but in this case, this kind of the bullseye of cold temperature doesn't exist in the climatology. So it shows some difference. But if this the count of a cold temperature is slightly moved to the westbound or eastbound or southbound, it doesn't really change the persistence of the diagram. So the same thing is true for this linear pattern. We know well, our human eyes recognize, oh yeah, these are the same patterns in this surface height and this surface temperature, but all the traditional methods, if you can always say that they are quantitatively different because the location of this wormhole is slightly different.
I think there is a question also in the chat on computational complexity from Nitai.
Nitai just Kyo just answered that question. Is there anybody else who has any other question? Please feel free to ask Kyo. Kyo has sharing us his time, so. Okay, Kyo, let me ask you a small question. Thank you for this presentation. It was very, very, very interesting. But my question is more about robustness. Do you think that using these TDA tools add more robustness to the methods that, I mean, to these applications on atmospheric sciences than previous approaches that you have seen that people is using in GPL or NASA?
So yeah, the robustness does matter because yeah, all the values displayed on Taylor diagram, like there's a, we know that what correlation is, and like we know the ratio of spatial standard deviation. So all of these numbers like have a certain like meaning, but the Barshstein distance is still relative matrix. So Barshstein distance of like a 10, what does it mean? Like so like Barshstein distance of 10 is like smaller than the Barshstein distance of 20, but still it is some kind of like a meaningless, like a matrix. So, and also about some sort of like a confidence interval, like I still, haven't found any like a clue and like how to interpret the Barshstein distance, the value itself. Like so, that's actually some challenging, and that's the biggest challenge of convincing the earth scientists to adopt the TDA in their analysis.
Oh, okay. So there is a period of time where we need to wait until it gets like certain acceptance, right? So any question from the audience?
Can I ask another question?
Yes, please.
Yeah.
One of the things that you are using, you have a reference map, and from reference map, which you are using as a climate, let us say, and you are talking about a new map, which you compare it to the climate map. And I think the climate map is based on an average of some sort.
Yeah.
So how one can determine this average itself? You see, I think when you are talking about a climate, you are talking about probably 10 years, 15 years, 20 years, and how do we determine the reference?
Yeah,
And
it is yeah. So there is World Meteorological Organization, they have a definition for climatology, and it is to generate the climatological mean, you need like 30 years of consistent observation. Then if you are averaging that, the observation over 30 years, then you can call it like a climatology. But unfortunately, this is a observation from satellite, and this satellite was under operation since 2004. So I only had less than 20 years of data, and I totally understand that depending on how many years of data I use to make an average, it can change this climatology map. Yeah.
I think the other thing which is connected with this is the question that was posed about robustness. Because if you have robustness of the original map, the climate map, and then you're talking about robustness in the current map. And I think this is quite interesting because you would be interested in seeing what direction things are going, I think, as far as robustness, because we are talking about average map. This means that we eliminated, I think, some of the extremes, I think, either the low extremes or high extremes, I think.
Yes.
Yeah. So it's quite interesting.
Yeah. So should think about that part. Yeah, I just took a note that so showing some sort of the robustness. Showing the robustness. And taking the approach of this deviation from the mean. Yeah, well, I will think about it.
Great. Thank you. Any other question from the audience? Okay, Julia.
No, I don't. I just don't say that we need to think. Yeah.
Yeah. Okay. So, well, thank you so much, Kyo, for this presentation. Julia, do you want to say some final remarks?
Yeah. I just let's make an upload to Kyo.
Yeah.
You can. Yeah. Thanks very much.
You can unmute and you can upload if you want.
Yeah. And thanks very much for joining this webinar series today. And the next talk will be on April 22nd. The speaker will be Frederick Siemens from Department of Geosciences of Princeton University. And I hope to see all of you there. Thanks very much.
Thank you. Thank you so much, everyone.
Thank you.
See you next.
Thank you. We enjoyed it.